Good afternoon, everybody. Uh, Thank you for taking the time out of your I'm sure, very busy schedules to join today's webinar. My name is Peter Rosinski. I'm a plastics engineer by education and now have a 30-year career focused on pretty much anything and everything to do with plastics material data science, plastics part design, injection mold design, injection molding, process theory and optimization, and then simulation of all of that. Coming up on my 15th year anniversary with Dassault Systems SolidWorks, and before this, I was 15 years with a company by the name of Moldflow Corporation. Anytime I do these webinars, I always like to start out with some high-level goals, and I hope today that you will learn some of the best practices for optimizing your plastics part designs for the injection molding manufacturing process. Actually, regardless of whether or not you use any simulation, there are some best practices you can follow to give yourself a good chance of success once your mold is in the machine. I will show you just a little bit about how you can use injection molding simulation to reinforce some of these best plastics part design practices, and then show you also a little bit about how you can predict and avoid some of the most common injection molding manufacturing defects using our injection molding simulation software, which goes by the name of SolidWorks Plastics. A little bit of housekeeping, some plastics materials terminology. You'll just like many other industries, we in the plastics industry have a lot of industry-specific terminology we use in our space. The first word I want to introduce, and please forgive me if I'm stating the obvious here, that's polymers. You don't even have to know what a polymer is, but you see in bold here that all the plastics that we ever talk about, they are all polymer materials, but not all polymers are plastics. So for example, you can have DNA, proteins, starch, cellulose. These are all polymers, they're not plastics. So what you'll find, a lot of us in the plastics industry, we use the words plastics and polymers interchangeably. So I hope that helps avoid any confusion. A next very common term that we use, especially related to injection molding, that's viscosity. I'm sure many of you are familiar with this term. May or may not be in the context of melted plastics, but in our world, viscosity, it's a measure of a melted plastic's resistance to flow. It's oftentimes directly related to the molecular weight of the plastic material. So the higher the molecular weight, the higher the viscosity, the higher the resistance to flow, the lower the molecular weight, the lower the viscosity, the easier it is for that material to flow. And then another term, kind of when we put some of all of these things together, I talk a lot about plastics melts or polymer melts or just melt in general. And of course, this is all in English here. Forgive me for my English, but when we talk about melts, again, especially related to the injection molding process, these are plastics materials that have been heated, melted, and mixed in preparation for injecting into a mold. Kind of a fun fact, polymer melts generally follow the path of least resistance. It's a really important thing to be aware of or to understand in the world of injection molding. And those paths of least resistance, if we're talking about the runner system of the mold, that would be, larger runners, larger diameter runners versus smaller diameter runners, or when you get inside the mold cavity, thicker wall sections versus thinner wall sections. So polymer melts, it's kind of like if they had a choice, they're always going to flow first through thicker or larger diameter runners. They're always going to flow first through thicker wall sections within your mold cavities. Okay, I always like to start out with some good news about plastics materials. Depending on what you hear or read in the news or media or social websites and so on, we all maybe know about or hear about this plastic island out in the Pacific Ocean. I always say that the plastic island in the Pacific Ocean, it's very much a pollution problem, not so much a material problem. Even if you could replace plastics with some other material, if we don't want these materials in our environment, then we have to keep the materials out of the environment. But the thing about plastics, they are probably the most versatile materials on the planet. And they enable technologies and products that allow us to do more with less material, reduce transportation cost, improve fuel efficiency. One of the best ways to improve fuel mileage in both in internal combustion engine automobiles or trucks is to make those vehicles lighter. Replacing metals with plastics, one of the best ways to do that in the automotive and the trucking industry. Plastics help us preserve food. It's one of the number one uses of plastics, packaging materials. Plastics help reduce injuries in all kinds of aspects of life, in automobiles and other kinds of transportation vehicles and all kinds of sports. Walk through any hospital today, guaranteed plastics are helping to save lives every day. They help protect fragile items in shipping, and they can be used to certainly contribute to circular economy and sustainability initiatives. My simple takeaways there is that I often say that plastics are and will continue to be very much part of the solution and really not so much part of the problem. Why do we use plastics in the first place? They're very lightweight materials. They have generally very high strength to weight ratios. Certain types of plastics have outstanding chemical resistance. I mean, there's certain kinds of applications in the world that just simply would not be possible without the chemical resistance of plastics materials. Plastics can have very high impact strength. They can be modified with rubber to achieve even higher impact strength. They are excellent insulators, all in terms of electrical, thermal, and noise. Certain plastics have excellent optical properties. Many lens applications today are basically wouldn't be possible without the use of optical grade plastics. They have relatively low manufacturing costs compared to some other materials. That's because the temperatures and pressures used to manufacture plastics tend to be lower than those required for other materials. And I'll talk a little bit more about this in a few minutes. Plastics can be very easily customized to meet very specific application requirements of lots of different kinds of products across a very broad range of industries. But not all plastics are created equal. So sometimes I'll talk to people out in industry, they think, plastic is plastic is plastic. But in fact, that really couldn't be further from the truth. Take this simple example here, polypropylene, probably the most widely used plastic on the planet. Three very common applications here: an automotive bumper fascia, an automotive instrument panel frame, and a living hinge cap. In fact, the living hinge cap, anytime you see such an application, any kind of a plastic product that has this built-in hinge, we call it a living hinge in the plastics industry. It's almost always that living hinge is only in parts that are designed and manufactured out of polypropylene. You can certainly have living hinges with other materials, but when you make a living hinge with another material, it's probably not going to last that long. Could be maybe just 5 cycles or 10 cycles or 20 cycles or something like that. One of the amazing things about polypropylene is that with the right kind of polypropylene and the proper design, you can get these living hinges to cycle maybe could be hundreds of thousands or 1,000,000 times or more, and it just never fails. It's due to the molecular structure of the polypropylene, but it's also just kind of an interesting fun fact. But you see these three applications here, very different, all polypropylene, but not all the same polypropylene. So you would have one grade or one formulation of polypropylene for the automotive bumper fascia. You would have so the bumper fascia, that's going to require some flexibility, some impact strength, UV resistance, chemical resistance. The automotive instrument panel frame probably going to require more stiffness and rigidity versus the automotive bumper fascia. And then again, the living hinge cap, maybe that's going to have some other application requirements besides just the living hinge, maybe some chemical resistance, maybe some sealing properties on the, the bottle that it screws onto. So all polypropylene, but I like to say 3 very different flavors of polypropylene. And then I mentioned this earlier. Plastics are one of the reasons why they're the most versatile materials on the planet is that they can very easily be customized or tailored to meet the very specific application requirements of lots of different kinds of products across a broad range of industry. We do that by adding the kinds of things that you see on this slide: colorants, UV stabilizers, antioxidants, foaming agents, other plastics. We can blend 2 or 3 compatible plastics together to get a completely different material than what we started with. We can add fillers, reinforcements, glass fibers, carbon fibers, graphite fibers to make those plastics materials even stronger. And again, this is a very short list here. This list could easily be hundreds of line items long. And the reason why, all of this so far is so important is because all of these different types of plastics, they have different properties and they process differently. So just if we look at some different families, polypropylene versus polycarbonate versus ABS versus high density polyethylene and so on, just each and every different family of plastic has different molecular makeup, different properties, and they require different temperatures and pressures and times at the injection molding machine. As I showed you with the example of polypropylene, just within a class or family of material, the properties and the processability can vary drastically. And then when we add fillers, additives, and reinforcements on top of all of that, it affects all of the above and kind of further complicates the situation. So don't forget any of that. Now we talk a little bit about injection molding, our primary manufacturing process of focus today. Why do we use injection molding in the first place? Some inherent advantages of injection molding. Number one, you can produce extremely complex geometry in what we call or refer to as net shape in English, net shape. Net shape means when your plastic part comes out of the mold, it has every feature required for its end use application, and you don't have to do any post molding or secondary manufacturing processes to finalize the features of your plastic part. So it means the color is molded in. It has all the geometric features required: ribs, gussets, bosses, through holes, vent holes, you name it. It's got the impact strength it needs. It has the mechanical strength it needs. It has the chemical resistance it needs, so on and so on and so on. So it's, that's really kind of an amazing benefit, when you think about it. Injection molding, it's a very high volume manufacturing process. This is one of the reasons why simulation can add so much value to the injection molding process. If you use simulation to save 5% of your material usage or shave a few percent off of your cycle time, because it is such a high volume manufacturing process, the cost savings can grow exponentially over time. So you're usually looking to produce hundreds of thousands, if not millions, of parts per year out of just one mold running in just one machine. The cycle times are typically fast, round about 3 to 4 seconds on the low end, and on average, maybe up to about 60 seconds on the high end. I don't think you can have cycle times much faster than about 3 seconds. Certainly, you can have cycle times much longer than 60 seconds, and that would be due to some special circumstances. Number one, it's a thick part, so the thicker your part, the longer it takes to cool. So the longer your cooling time, the longer the overall cycle time. And then you can have other complications in the process where it may, because of the part geometry and the mold geometry, it may just take some time to safely extract the molded part from the mold. So, just taking the part out of the mold can add some additional seconds to your cycle time. And when all is said and done, when your part finally comes out of the mold, so when you add up the cost of designing the part, designing the mold, making the mold, buying the machine, running the machine, buying the plastic, and all of that, because these molds produce so many parts in such a short period of time, and then these molds can have a very long lifetime, could be 5 or to 10 years or more. When the parts finally come out of the mold, they're usually coming out at what I call pennies on the dollar or cents on the euro. So it could be 3-cent euro, 5-cent euro, 10-cent euro, and so on. Some injection molding process terminology that we use in the plastics industry. I mean, this is kind of injection molding theory 101. Once the melted plastic is ready to inject into the mold, the first thing that happens is what we call first stage injection. So the screw of the injection molding machine moves forward, fills the mold cavities, typically to about 97 or 98% of their volumetric capacity. It's what we call a velocity controlled phase of the process. So you're generally just looking to inject the plastic as fast as you possibly can without damaging the plastic material and without exceeding the maximum injection pressure capability of the injection molding machine. After first stage injection, we immediately move into second stage injection, commonly referred to as the packing phase or the holding phase of the process. This is when we hold pressure on the entire system to complete mold filling to 100% of the volumetric capacity of the mold cavities, and to compensate for shrinkage that occurs. In general, every injection molded part shrinks. So we want to use the packing or the holding phase of the process to compensate for that shrinkage and maybe try to minimize the amount of shrinkage as much as possible. That second stage pressure, it's released only after the gates freeze off. There are some exceptions to that rule, but by and large, we wait till the gates freeze off. That's so that if there's any molten or melted plastic still in the mold cavities, if the gate is frozen off, that prevents any of that melted or molted plastic from escaping the mold cavities. I'll talk a little more about gates in a few minutes. And then we go into the cooling phase. This is just we just have to wait, right? We have to wait until the part is cooled to a temperature that is safe for ejection. So that those plastic parts, when they come out of the mold, they're still pretty hot, but generally we wait until it's cooled to a temperature so that the part has enough structural integrity so that it won't deform when it comes out of the mold. The other thing that happens during the cooling phase is the injection molding machine is preparing the next shot of melted plastic for the next cycle. Once the parts are cooled to a safe temperature, the mold opens and the parts are often mechanically ejected. They're pushed out by ejector pins. Sometimes they're pushed out by air. Other times a robot comes in and removes the parts from the mold. So that's, the basic overview of the injection molding process. Now, just a little bit about injection molds. These are high precision instruments. They can be extremely complex. They don't come cheap. They can cost tens of thousands to hundreds of thousands to over €1 million for just one mold. And you can imagine that the more expensive your mold, the more costly the design mistakes might become. Some injection mold terminology. What you see here is a standard 2-cavity cold runner system injection mold layout. If we dig a little bit deeper into this, the first piece of geometry that we talk about is the sprue. The sprue is the interface between the injection molding machine and the mold. So, the last component of the injection molding machine that the melted plastic sees is what we call the nozzle in English. When the melted plastic comes out of the nozzle, it enters the sprue of the mold. The sprue then connects to the runner system. You can have primary runners, secondary runners, tertiary runners, and so on. The runners basically connect the sprue to, let's say the runners get very close to your mold cavities. The runners then interface to what we call the gate, right? So the gate is the last piece of geometry that the melted plastic sees before it enters the mold cavity. One important thing to know about gates is that they can, more often than not, they are probably the thinnest cross-sectional area that the melted plastic has to travel through. And of course, once the plastic goes through the gate, it enters the mold cavities. Those are formed by the mold cores and cavities. May seem or sound all kind of simple, but when we start to add all of this up, the reason why injection molding simulation software has had a viable market for better part of 40 years now is that injection molding, it's a complex mix of time, temperature, pressure, material, part geometry, and tooling variables. Just so you can see how some of the ways that the process gets kind of complicated. If we could make part design changes, we can make mold design changes, we can make material changes, and then we can change process parameters at the injection molding machine, right? So we can change times, temperatures, and pressures at the injection molding machine. I like to preface all of this by saying all things being equal. So all things being equal, if I increase my part wall thickness, so I change my part design, I increase the part wall thickness, guaranteed the pressure required to fill that mold will decrease, but my cooling time will increase. So I made my part thicker, it takes longer to cool. That's going to add some seconds to my cooling time and then my overall cycle time. So it may sound like a trade-off, but in this case, because I made my part thicker, I might get a better quality part. My part might be stronger. It might have lower molded in stress. It might actually be less likely to warp or deform out of shape. So I pay a price of increased cycle time, but I might get a higher quality part. Conversely, if I decrease my part wall thickness, if I determine through structural simulation that I can reduce my wall thickness by 10 or 15% or something like that, again, all things being equal, my pressure required to fill will increase. So now I'm going to have to make sure that I don't exceed the maximum injection pressure capability of my injection molding machine. But since I made my part thinner, it doesn't take as long to cool. That's going to decrease my overall cycle time. This list could go on and on and on, but here jumping to the bottom, if I add colorant to my plastic material, you see pressure required to fill could go down, could go up. We actually don't always know. This is because sometimes when you add a colorant to a plastic material, that colorant may decrease the viscosity of the melted plastic. Remember that the term viscosity. So I could add a colorant to my plastic material, which decreases the viscosity. That would, all things being equal, that would require lower pressure to fill. And I've certainly seen many cases in the past where we add a colorant to a plastic material where it actually increases the viscosity of the material. It increases the resistance to flow, requires higher pressures and maybe even temperatures at the injection molding machine. And then the final line item there, reinforcements, glass fibers, carbon fibers, graphite fibers. These, pretty much all the time increase your melt viscosity. They increase the resistance to flow. They require higher pressures to fill, often higher melt temperatures to fill the mold. However, you get a much stronger part that usually also has higher temperature resistance. pardon me for that, as you now might imagine, plastics part and injection mold design mistakes can be very costly and time consuming. Surveys that we've run in the past, we ask a simple question. These are people, professionals who are involved in some aspect of the injection molding design to manufacturing process. How many rounds of mold rework are required before you can produce acceptable quality parts out of your molds? You can see the statistics here and make what you will of them. And I don't know what ones you would find alarming. 39% of the time, at least 2 rounds of mold rework. 23% of the time, at least 3 rounds of mold rework. 7% of the time, at least 4 rounds or more of mold rework. Maybe the most alarming statistic, 6% of the time, the mold never works. Now, I don't know if you believe these statistics or not. I can tell you just within the last 24 hours, and I'm a guy with a 30-year career in the plastics industry. Yesterday, I had a customer slash prospect call. I can't mention any names here, but this is a really good SolidWorks 3D CAD customer. Basically designing all of their plastic parts using SolidWorks 3D CAD. It's a company which has been around for decades. They're part of a large conglomerate out of the Asia Pacific, which is doing close to 6 billion euro a year in revenue. And they're considering investing in injection molding simulation. And one of the primary reasons for that is that the customer they're designing all of their plastic parts in-house. But then when it comes time for the mold design and the mold manufacture, they're relying on outside suppliers for that. So they basically take their part designs, they throw them over the wall to the mold designer. The mold designer uses their experience and expertise to design the mold. And in the design review process, in the mold design review process, the customer here, the company which is designing the plastic parts, they're relying on the expertise of the mold designer because they don't have a lot of mold design expertise in-house. And one of the biggest topics of discussion or the design review consideration, it's just simply the gate location. Where should the part be injected with plastic material, with the melted plastic? So they kind of scratch their heads. They look at the proposed design. Everyone says, looks good. So they move forward with the mold manufacturer. They get the mold made. They put the mold in an injection molding machine. They load it up with plastic granules. They start the process. And then no matter what they do with the injection molding machine, so no matter how fast or slow they inject, no matter what pressures they use, no matter how long they hold second stage pressure, no matter what the cooling time is, they just simply cannot get good parts out of this mold. It's kind of amazing, but this just happened within the last 24 hours. So when I hear that kind of a story, almost on a day-to-day basis, I see these kinds of statistics. This is what makes me realize that I will never be able to retire because it's been 30 years and these problems are still happening. I think I have another 30 years in me. So what can go wrong? Now I'll show you just some of the most common injection molding manufacturing defects that can be predicted, analyzed, and avoided with injection molding simulation. I mean, I'd like to say that these problems were solved decades ago, really 40 years ago, I think. We started to develop a good understanding of how these melted plastics flow into a mold, and what injection molding simulation does for you. It basically gives you a window into your mold so you can see what's happening. Number one, short shots. It's the term that we use in English. Short shots. If you think about these molds, pretty much every mold that you have, you always want to fill and pack it to 100% of its volumetric capacity. Sometimes that doesn't happen. Sometimes the mold, no matter what you do with the injection molding machine, the mold can only be filled to 95% of its volumetric capacity, or 90%, or 85%, or something less than that. The thing is, if we're not using simulation, we don't always know what the cause is. And that's because there's multiple causes of short shots. Could be simply a bad gate location. Could be that we're gating from thin to thick and the melted plastic is cooling off, maybe even freezing before it can fill and pack the thick sections of the part. Could be that there's just not enough gates. We're trying to fill a part with one gate, and it turns out we need two gates because of the size of the part and its geometry. Could be that we're exceeding the maximum injection pressure capability of the injection molding machine. Now, that might mean that we might have to move to a higher pressure machine, or we might have to open some things up to reduce the pressure requirements. Means if we could be something like we just increase the size of the sprue or the diameters of the runner system, or we increase the thickness or the diameter of the gate a little bit. All of those things will lead to decreasing the pressure required at the injection molding machine. Could be our melt temperature is a little bit too low, or the mold temperature is a little bit too low, so we could play with temperatures. Could be that we're not injecting fast enough. Our first stage injection is just simply not fast enough, and again, the cooling effects inside the mold are taking over before we can properly fill and pack the mold. Could be that we're just using the wrong plastics material. And what I mean by that, if we take polypropylene as an example, we can have very high flowing grades of polypropylene. We can have medium flowing grades, or what we call stiff or low flow grades of polypropylene. Now that's, again, a lot of times simply due to the molecular weight of the material. So it could be that we might have to just move from a higher molecular weight formulation of polypropylene to a slightly lower molecular weight that will have lower viscosity, lower resistance to flow. Now we can properly fill and pack our mold. So it's kind of amazing, just one defect here, multiple causes, often very difficult to know what the exact cause is unless you're using simulation. Good news in a product like our SolidWorks Plastics, we have this thing called a results advisor for pretty much any injection molding simulation result that we generate. You can go in this results advisor, you get some insight as to why the problem might be occurring, and then some suggestions for possible solutions to fix the problem. Weld lines and air traps. Weld lines, these are areas inside your mold where two or more flow fronts come together. They can cause both cosmetic and or structural defects. That's because the main thing here is that weld lines are never as strong as areas of your part that do not have weld lines. And the thing about weld lines is that, sometimes the best you can do is that they have like 40 to 60% of the nominal strength of the rest of your part. And the other thing about weld lines is you can often see them. They appear as just like a line, or what you might call a ghost line, or a crack in the molded part. That may or may not be a problem. The cosmetic defect may or may not be a problem, depending on the surface appearance requirements of your part. The other another defect that can occur as the melted plastic fills the mold. If you think about these mold cavities, before they get filled with melted plastic, they're filled with air. That's when the mold closes, atmospheric air just gets trapped in there. As the melted plastic flows into the mold, the trapped air has to have somewhere to go. Usually it's just vented out the parting line of the mold and it doesn't cause a problem. But sometimes that you can have air that gets surrounded by the melted plastic. It gets compressed as the mold continues to fill and pack. And if it gets compressed enough, there's a small explosion or combustion inside your mold cavity. If it gets to that point, and by the way, this is a completely unacceptable defect. If it gets to the point where you get the small explosion, that will cause a burn mark on your part. It more than likely will cause an unintended through hole, and that little explosion is usually going to damage your steel core and cavity surfaces. So that's one you really want to avoid. Here is on this application, on this product, we're plotting the weld line and the air traps that occur in this part. The way that the melted plastic flows into this mold, we get a racetrack effect around the thick rib that runs around most of the perimeter. So as that melted plastic fills in, it takes the path of least resistance. You remember that phrase. The path of least resistance is the thick rib that runs around the perimeter. That sets up two flow fronts that come together in the middle of this part. Even though there's no through holes, even though there's only one gate, we still get this massive weld line. We get air that gets trapped, surrounded by plastic. This is, again, an unacceptable defect here. And then down the end, we get another air trap prediction, which I like to think of as a vent location. So, anytime you get air trap predictions around the perimeter of your part, those are the ideal locations, or like the minimum locations that you should include venting to atmosphere. Sink marks. Sink marks are surface indentations which are caused by excessive shrinkage in localized thick sections of the part. Usually they occur at the base of reinforcing ribs. So that where the base of the reinforcing rib is just simply too thick. Those you can also get these localized thick sections due to bosses or gussets. And we'll talk about the some rib design guidelines in a few minutes. This is a problem which is generally very easily predicted and analyzed and avoided. And then maybe the ultimate one of the ultimate defects that occurs in injection molded parts, part warpage. This is when you're just trying to simply mold some kind of a flat part, and when the part comes out of the mold, it's shaped like a potato chip or a tortilla chip or something like that. There's multiple causes of part warpage. So this is the other thing, right? Even if your parts are warping, if you're not using simulation, it's very difficult to know if the part is warping simply due to non-uniform molded in stress, non-uniform cooling, or non-uniform volumetric shrinkage. Or then we can start to complicate matters by looking at fiber orientation and the resulting mechanical properties and what happens there. You can see this all gets kind of complicated in a hurry, and if you're not using simulation, I think it's a lot of head scratching and trial and error. So now to the heart of the content of today's webinar: the 7 best practices of plastics part design for injection molding. Again, that's the primary process that we're focused on here today. So not extrusion, not blow molding, not rotational molding. This is predominantly for injection molding. Number 1, if you did nothing else, maintain uniform wall thickness, and I'll go through each of these in more detail. Number 2, avoid abrupt thickness transitions. So if you cannot maintain 100% uniform wall thickness, or within let's say plus or minus 10% of your nominal wall thickness, you always want to try to avoid abrupt thickness transitions. Make those nice and gradual. I'll give you some rib design guidelines, some very easy to follow rules of thumb. So even if you're not using simulation, this will help you design and manufacture better reinforcing ribs in your plastics parts. Determine the optimum material candidates. As I mentioned earlier, sometimes you might just have to move to same material, but one that's slightly lower molecular weight that flows a little bit better into your mold cavities. This is could easily be at the top of the list: gate from thick to thin. I'll go into more detail on that one. Make sure that you size your gates properly. I can't tell you how many times I see a problem where that's the simple problem is that everything else is generally okay, but the gate is just way too thin. So the thickness or the diameter of the gate is just way too thin for the mold cavities to be properly filled and packed. And then number 7, always try to minimize weld lines, due to the fact that they can be structural defects in your part. So now digging into the detail. Number 1, maintain uniform wall thickness. Typical or average wall thicknesses for injection molded parts, usually in the range of about 2 millimeters to 4 millimeters. You can certainly have thinner parts than that. Maybe the minimum limit is about 1/4 of a millimeter or 10,000ths of an inch. You can certainly have much thicker parts than 4 millimeters or 160,000ths of an inch. You could have parts that are 5, 6, 7, 8 millimeters thick, maybe even more than that. And no real problem with that. But you just have to understand that, number one, cycle time will go up exponentially. That's because your cooling time will go up exponentially as part wall thickness increases. But again, on the other hand, I mentioned this earlier, for certain types of applications, you may need a thicker part for that geometry and material combination to meet your end-use application requirements. This very simple example here, we have, our nominal wall thickness is 2.5 millimeters. The way this part is initially designed with these sharp corners, we wind up with a localized increase in wall thickness that goes up to 3.5 millimeters. This is something that you want to avoid. Simple fix for that, you add radii both on the inside and the outside of that. You break the sharp corner, you add radii. Now you have a nominal 2.5 millimeter wall thickness throughout. So, simple, very simple example, kind of a very simple design hint and tip, but, one that can be applied to, lots of different products across lots of different industries. Number two, avoid abrupt wall thickness transitions. So again, if you can't maintain uniform wall thickness within, certain tolerances, if we just look at the graphics here on the right-hand side, number one, this is kind of the worst case scenario. You've got a sharp corner. These sharp corners within, that are inside the body of your plastic part, they will always be stress concentrators. So you always want to avoid sharp corners almost no matter what, because they can cause other problems down the road. If we move down the graphic here, the number two, that's a little bit better. We've chamfered the sharp corner. Still not a great solution. Number three, a little bit better. We've made the transition from thin to thick a little more gradual. But the fourth iteration here is really the best. What you want to do is core out your thick section so that now you just have a nominal wall thickness, throughout your part. And if I had to summarize, kind of this whole paradigm here, uniform wall thickness, that results in uniform filling of your mold cavities. That leads to uniform packing. That leads to uniform cooling. That leads to uniform molded in stress, uniform volumetric shrinkage. That tends to minimize your molded part warpage and just give you a part that has better part quality. So, you can now understand why we often say, number one, if you did nothing else, just try to maintain uniform wall thickness of your part. So even if you don't get the gate location right, even if you're not doing the best things at the injection molding machine, uniform wall thickness will give you always the best chance of success at the molding machine. Follow rib design guidelines. I mentioned this earlier, what can happen at the base of these reinforcing ribs is that you get a localized, if the base of your rib is too thick, you get this localized increase in wall thickness. As that material cools and shrinks, it shrinks in upon itself. It pulls in on the surface of the part. So the surface of the part sinks in, or you get this depression, and in English we call it a sink mark. Here's an example here. We have this handle with these reinforcing ribs. This is just showing you the exterior and the interior of the handle, where the base of the ribs is the same thickness as our nominal wall thickness, 2.5 millimeters. And then what you're seeing here is our sink mark predictions. So these green or light green lines that you see, these are the sink mark predictions. So again, on the left-hand side, the base of my ribs is my nominal wall thickness. It's 2.5 millimeters. We reduce it to 80% of the nominal wall thickness. We make it 2 millimeters thick at the base of the rib, and you can already see that the sink marks are starting to fade. We take that a step further and make the base of the ribs 50% of our nominal wall thickness. So now the base of the rib is 1.25 millimeters thick, where it meets the nominal wall. And you can see that our sink marks have, let's say, all but disappeared. So, now you get the idea. If the base of your ribs is too thick, you're almost certainly going to have a sink mark problem. And keep in mind, because the root cause of this problem is that there's not enough plastic material packed into those areas to compensate for the shrinkage. It's actually going to make the ribs a little bit weaker. So you're kind of defeating the purpose of having a reinforcing rib in those locations. So the simple rule of thumb rib design guidelines. Number one, the base of your ribs should be somewhere around 50 to 70% of your nominal wall thickness. I mean, I showed you how we went from 100% down to 50%. We make the sink marks practically disappear. Rib height, 2.5 to 3 times your nominal wall thickness. Ribs, they need draft so that you can eject them from the mold, 0.5 to 1.5 degrees of draft per side. You should have radii at the base of your ribs. The radii should be 25% to 40% the dimension of your nominal wall thickness. And then the distance between your ribs should be at least 2 to 3 times your nominal wall thickness. If your ribs are too close together, that could cause another problem. You can get localized localized relatively hot spots inside your mold cavities, which can then lead to another whole set of problems. Determine your optimum material candidates. I mentioned this earlier. Sometimes you might have to just move from a higher molecular weight polypropylene to a slightly lower molecular weight polypropylene. Our injection molding simulation software has a material database of some 4,000 plastics materials that allows you to try out different what-if scenarios so that you can try different material candidates in your applications to see if maybe just changing the material might be the solution to the problems. Gate from thick to thin. I can't tell you how many times I continue to see this problem where up in the upper left-hand corner here, you have a mold design so that the gate location is in sometimes the thinnest areas of the part. And what happens is that the melted plastic cools off too much or even freezes. It freezes off before the thick areas of the part can be properly filled and packed. On the right-hand side of the graphic, it's what I would call a Band-Aid solution or a cheat solution. Sometimes it's the only option that you have, though. We add what's called a blind runner to your part geometry. So we're actually adding material to the mold cavities to improve flow through the thin section so that thin section, you allow material to get through there and fill and pack the thick section before it can cool and freeze off. Not a preferred approach because that's you're going to be adding more material when you don't really have to. It serves no functional purpose other than to get the mold cavities to fill and pack. And then you may also pay a price in increased cycle time because now that geometry is going to take longer to cool off before you can eject it from the mold. The preferred solution, bottom left-hand corner, just gate from thick to thin, and you're going to be avoiding most of the potential problems that could occur. Size gates properly. There's a simple rule of thumb here I'll give you in just a few seconds. There's all kinds of different gate types out there. There's edge gates, submarine gates, pin gates, fan gates, tab gates, diaphragm gates. But when I think about gate geometry, I think of some thin cross-sectional area that the melted plastic has to flow through. It's usually just it's some thickness or it's some diameter. And the simple rule of thumb for gate sizing is that your gate thickness or gate diameter should be somewhere around 50 to 90% of your part's nominal wall thickness. I can't tell you how many times I see this problem where the gate is only 20 to 30% of the nominal wall thickness. So everything else is okay. Part design is okay. Mold design is generally okay. The gate is just too small to be able to fill and pack the entire mold cavity before the gate itself freezes off and you can't transmit any more pressure to your mold cavities. Number 7, minimize weld lines. Remember, weld lines, they can also be called knit lines or meld lines in English. They're places inside your mold cavity where 2 or more plastic flow fronts come together. They can be structural defects because they pretty much never have the nominal the nominal strength of the rest of your part. Remember, they could easily only have like 40 to 60% of your nominal wall strength, and in worst case scenarios, they can have much less than 40% of your nominal strength. They can also cause cosmetic defects because you can usually see them. So that's another consideration. The simple recommendations there: minimize the number of gates. So I mean, in most plastic parts, you always try to start off with, if you can. I mean, basically, if you can fill your part with one gate, you fill the part with one gate. So only if you absolutely have to use two gates, you use two gates. You can see on the left-hand side of this graphic here that the minute you introduce a second gate, you introduce a weld line or a knit line. So that's just something to keep in mind. And then the other thing that you can do is, if weld lines are absolutely unavoidable inside of your part geometry, you can use injection molding simulation to play with your gate location to try to move your weld lines to non-critical areas of your part. Just a brief introduction of our injection molding simulation software. We call it SolidWorks Plastics. We're just fundamentally simulating the flow of melted plastic into injection molds. We basically give you a window into your mold that helps you predict and avoid these common injection molding manufacturing defects. It will help you to eliminate costly and time-consuming mold rework, improve part quality, and if all of that is happening, you'll be able to decrease your time to market. The value proposition, it's simple, it's clear, it hasn't changed for decades. At least 80% of the plastic parts that you come into contact with on a daily basis are manufactured by the injection molding process. Remember, injection molding, it's a very high volume manufacturing process. So if you can use simulation to shave off a little bit of your cycle time or reduce a little bit of your material usage, your cost savings over time grow to be exponential usually. Injection molding, it's a complex mix of time, temperature, pressure, material, design, and tooling variables. My simple takeaway there: very difficult to figure out inside your head how that melted plastic will flow inside the mold, especially as your part geometry gets more complex and the materials that you're using get more sophisticated. And then those injection molds can be very costly. They can range anywhere from tens of thousands to hundreds of thousands to over €1 million for just one mold. And so you could imagine that using injection molding simulation to avoid just one round of mold rework on a very expensive mold, more often than not pays for one or more licenses of the software. To summarize all this, don't forget about the 7 best practices of plastics part design. Try to maintain uniform wall thickness when and if possible. Avoid, if you cannot maintain uniform wall thickness, if you have to have a mix of thin and thick sections, try to avoid abrupt transitions between thin and thick and vice versa. Follow those rib design guidelines. Number 1, the base of your ribs should be about 50 to 80% of your nominal wall thickness. Determine the optimal material candidates. Sometimes, again, you might only have to change the material to get your molds to fill and pack properly. Gate from thick to thin when and if possible. Again, that's one that is it's a big problem I see a lot, where the gate is into the thinnest section of the mold cavity, and no matter what you do with the injection molding machine, you just can't get that mold to fill and pack before the material cools and freezes off, before it can properly reach the thick sections of the part. Size gates properly. Gates should be somewhere around 50 to up to 90% of your nominal wall thickness. That depends a lot on the material that you're using. And then when and if possible, try to minimize or eliminate weld lines if you can. Key takeaways: because plastics are the most versatile materials on the planet, their production and use will continue to grow for the foreseeable future, certainly in all of our lifetimes. Plastics materials enable environmentally friendly and sustainable technologies and products, so they will continue to be very much part of the solution and really not so much part of the problem. And because injection molding is such a complex process, it requires products like SolidWorks Plastics to predict and avoid those manufacturing defects, eliminate costly mold rework, optimize your part design, mold design, and the injection molding process itself, decrease time to market, make better products, and so on. So that's the end of my main content. Again, I sincerely thank you for taking the time out of your busy schedules to attend. Thank you. Vielen Dank. And I hope you have a great rest of your day and a safe, enjoyable, and relaxing weekend with your family and friends. Thanks und auf Wiedersehen.